What if everything you've ever believed about time is wrong? Right now, as you listen to this, billions of clocks across the planet appear to be ticking together. The second hand moves, hearts beat, planets orbit, the sun rises and sets with comforting regularity. It all feels as though the entire universe is sharing one enormous cosmic clock, but it isn't. Some clocks are aging more slowly than others at this very moment. A clock aboard a satellite is not keeping time at the same rate as one resting on Earth's surface. An astronaut traveling at extraordinary speed would return having experienced less time than the people who stayed behind. And near a black hole, time itself can slow to such an extreme that hours for one observer could correspond to years or even centuries for someone else. This isn't science fiction, these are real, measurable consequences of the laws that govern our universe. The deeper physicists investigated reality, the stranger time became. They expected to uncover a universal clock quietly ticking behind every event in existence. Instead, they discovered something far more unsettling. The universe has no single master clock. Motion changes time. Gravity changes time. Even the idea of now something that feels so obvious in everyday life turns out to be surprisingly complicated. For centuries, humanity believed time flowed like an invisible river, carrying everything forward at exactly the same pace. It seemed absolute, predictable, and shared by everyone. It told us when to wake, when to sleep, when seasons would change, and how the heavens moved. Above our heads, it felt like the one thing in the universe we could always trust. Yet modern physics tells a completely different story. Time is not simply the background against which the universe unfolds. It is part of the universe itself. It can stretch. It can slow down. It can be shaped by gravity and motion. Under the right conditions, two people can follow different journeys through the cosmos and genuinely experience different amounts of time before meeting again, and somehow, despite all of this, we continue to experience life as though time flows in only one direction. We remember yesterday, but not tomorrow. A broken glass never leaps back onto the table. Smoke never gathers itself and returns to the flame. The past feels fixed. The future remains uncertain, and the present slips away almost before we realize it exists. So what exactly is time? Is it a physical substance? A dimension woven into the fabric of space? A consequence of entropy? Or could our deepest understanding of reality still be missing something fundamental? Tonight, we're going to follow one of the most remarkable scientific journeys ever undertaken. We'll begin with the simple clocks built by ancient civilizations, travel through Newton's elegant vision of an orderly universe, witness Einstein's revolutionary discovery that transformed time forever, and explore the astonishing physics of relativity, black holes, entropy, and the unanswered questions that continue to challenge the brightest minds in science, because by the end of this journey, you may realize that the greatest mystery isn't whether time exists, it's why the universe experiences it at all. To understand time, we first have to forget almost everything our intuition tells us about it. Time feels obvious because we've lived inside it for our entire lives. We measure it with clocks, organize our lives around it, celebrate birthdays, count down holidays, and watch years quietly disappear. It seems so ordinary that we rarely stop to ask the most fundamental question of all. What is time, physically? Notice that this isn't the same as asking what time feels like. The feeling of time belongs partly to memory, consciousness, biology, and the remarkable way the human brain organizes experience. Physics approaches the question differently. It sets aside emotion and perception for a moment and asks something much quieter. What can actually be measured? At its most fundamental level, physics doesn't measure time directly. It measures change. A heartbeat marks change. A swinging pendulum marks change. The steady drip of water marks change. The rotation of Earth, the orbit of the moon, the motion of planets, and even the tiny vibrations inside atoms are all repeating physical processes. Every clock ever built, from the earliest sundials to today's atomic clocks, works because something in nature repeats with extraordinary regularity. This leads to one of the most important ideas in all of physics. A clock does not capture time. It compares one repeating physical process with another. A mechanical clock counts the rotation of gears. A pendulum clock counts the steady swing of a weighted arm. A quartz watch counts the incredibly regular vibrations of a quartz crystal when electricity passes through it. And the most accurate clocks ever created count tiny quantum transitions inside atoms such as cesium. whose behavior is so stable that modern science uses them to define the second itself. The more stable the repeating process, the more accurate the clock becomes. Long before modern science, people had already discovered this principle. By simply looking upward, the rising and setting of the sun defined the day, the changing phases of the moon created the month, the slow return of the seasons shaped the year. Ancient civilizations built sundials that tracked the shadows across stone. They designed water clocks that measured the steady flow of liquid from one vessel to another. Farmers relied on the heavens to know when to plant and harvest. Sailors navigated by the stars. Entire civilizations synchronized their lives with the predictable rhythms written across the sky. In many ways, astronomy became humanity's first great clock. As science advanced, time became even more essential. Describing motion requires more than knowing where something is. You must also know when it is there. Speed is simply distance divided by time. Acceleration is the change in speed over time. Planetary orbits, falling objects, sound waves, electrical signals, collisions, gravity, and nearly every equation in physics depends on the ability to compare one moment with another without time. The universe would contain positions but no motion, events but no sequence, causes but no effects. It would be like reading a book whose pages had been scattered across the floor, with no page numbers to tell you what came first. Time also allows physics to connect the unimaginably small with the unimaginably large. Inside your body, electrical impulses race through nerve cells in tiny fractions of a second. Inside an atomic clock, billions of quantum oscillations occur with astonishing precision. Meanwhile, planets spend months or years completing their orbits. Stars shine for millions or even billions of years, and the universe itself has been evolving for approximately 13.8 billion years since its earliest observable moments. Across every one of these vastly different scales, time is never measured by a mysterious invisible substance. It is always inferred through regular, repeatable physical change. But hidden inside this seemingly simple idea lies a question that would eventually overturn centuries of scientific certainty. If every clock is itself a physical object made of atoms moving through space, affected by gravity, and subject to the laws of nature, why should every clock always agree with every other clock? Is there truly an invisible cosmic time flowing independently behind the universe, while clocks merely attempt to follow it? Or is time nothing more and nothing less than the behavior of physical systems themselves? For more than 200 years, science believed it already knew the answer, and that answer had a name: Isaac Newton. For Isaac Newton, the universe was an extraordinary machine, not a machine made of steel and gears, but one built from elegant mathematical laws that governed everything from an apple falling from a tree to the motion of the moon around the earth and the planets around the sun. Beneath all of this motion, Newton imagined something that never changed, never accelerated, never slowed down, and never depended on who happened to be observing it. He called it absolute time. According to Newton, time existed independently of everything else. It flowed uniformly throughout the entire universe, completely unaffected by matter, motion, or gravity. Whether a person was standing still, sailing across an ocean, riding in a carriage, or watching the stars from a quiet hillside, the same invisible cosmic clock continued ticking for everyone. Clocks could be inaccurate, pendulums might swing imperfectly, water clocks could drip unevenly, even the Earth's rotation was not perfectly constant, but those were merely flaws in the instruments. The true flow of time, Newton believed, remained perfectly steady beneath them all. It was an idea of breathtaking simplicity, and for centuries, it worked astonishingly well. Imagine throwing a ball across a field. Newton's equations could predict exactly where it would land, fire a cannon. His mathematics could calculate its trajectory with remarkable precision. Watch the moon circle the Earth or the planets travel around the sun. The same laws explained them all. For the first time in history, the heavens and the Earth were no longer separate worlds governed by different rules. The apple and the moon had become part of the same cosmic story. This was one of the greatest intellectual triumphs humanity had ever achieved. Motion became something that could be calculated, predicted, understood, and at the center of every calculation sat one silent assumption: time flowed equally for everyone. Different observers might disagree about motion. Someone standing beside a road would say a carriage was moving. Someone sitting comfortably inside the carriage might insist they were perfectly still while the landscape rushed backward. A sailor Aboard a smoothly sailing ship could drop a stone and watch it fall straight to the deck. An observer standing on the shore would describe the very same stone, following a graceful curved path through the air. Both descriptions were correct. They simply belonged to different points of view. Yet despite these differences, Newton believed both observers still shared exactly the same time. 1 second for one person was 1 second for everyone else. That shared clock made the universe beautifully predictable. It became the invisible stage upon which every event unfolded. Even today, that picture remains incredibly successful. Drive a car, launch a firework, or calculate the orbit of a satellite under many everyday conditions. Newton's laws work so well that they often appear almost perfect. This is an important point. Newton wasn't wrong, he was incomplete. His theory describes the everyday world with remarkable accuracy, because almost everything we experience moves incredibly slowly compared with the speed of light, and almost every gravitational field we encounter is relatively weak. Our intuition grew up inside that comfortable world. We naturally expect clocks to agree. We naturally believe that now means the same thing everywhere. We instinctively imagine the entire universe sharing one enormous cosmic present. Nature, however, had been hiding a secret in plain sight. It was traveling across the universe every moment. It illuminated every sunrise, every distant galaxy, every star in the night sky, every candle flame, every reflection in a mirror. It was light. At first, light seemed perfectly ordinary. It could be reflected. It could be bent by glass. It could be separated into the colors of a rainbow. Newton himself believed light was made of tiny particles streaming through space. Others argued that it behaved more like a wave. For generations, scientists debated which picture was correct. Then, during the 19th century, an extraordinary breakthrough changed everything. Scientists studying electricity and magnetism began noticing something remarkable. Electric charges could create magnetic fields. Changing magnetic fields could generate electric currents. These two invisible forces, once believed to be completely separate, turned out to be deeply connected. No one understood that connection better than the Scottish physicist James Clerk Maxwell. Using an elegant set of mathematical equations, Maxwell unified electricity and magnetism into a single theory. But hidden inside those equations was an astonishing surprise. They predicted the existence of waves capable of traveling through empty space. When Maxwell calculated the speed of those waves, he discovered something extraordinary. The number matched the known speed of light almost perfectly. Light wasn't merely something that traveled through space. Light itself was an electromagnetic wave. It was one of the greatest discoveries in the history of science. But it also created a problem that no one saw coming, because Maxwell's equations didn't merely describe light. They assigned it a very specific speed, not approximately. Not depending on the observer. A single, fixed speed built directly into the mathematics of nature itself. And that simple fact would soon force scientists to question one of the oldest assumptions in physics. What if time itself wasn't as absolute as Newton had believed? At first, the problem seemed almost too small to matter. After all, speeds had always behaved in a perfectly reasonable way. If you're standing beside a road and a car drives past at 60 kilometers per hour, that's the speed you measure. If someone inside that same car throws a ball forward at 20 kilometers per hour, an observer standing on the roadside naturally concludes that the ball is moving at about 80 kilometers per hour. One speed simply adds to another. It is such an ordinary part of everyday life that we rarely stop to think about it. The same idea applies almost everywhere. Walk toward the front of a moving train, and someone standing outside measures your speed as your walking speed plus the train's speed. Swim with the current of a river, and your speed relative to the riverbank increases. Ride a bicycle with the wind behind you, and everything feels exactly as common sense suggests it should. For centuries, no one had any reason to doubt this simple rule. Surely light should behave the same way. If a flashlight is switched on inside a moving train, shouldn't someone standing beside the tracks measure the light as traveling slightly faster than someone riding inside the train? According to Newton's picture of the universe, the answer seemed obvious. Yes, but Maxwell's equations quietly insisted on something entirely different. They predicted that light always travels through a vacuum at the same speed, approximately 300 kilometers every second, not the speed of the lamp, not the speed of the observer, a speed built into the very fabric of electromagnetism itself. That immediately raised a deeply uncomfortable question. 300,000 kilometers per second. Relative to what? At the time, nearly every known wave required something to travel through. Sound waves needed air. Ocean waves needed water. Vibrations needed a rope, a string, or some other material. So if light was truly a wave, scientists naturally assumed it must also have a medium. They proposed an invisible substance filling all of space. It was called the luminiferous ether. According to this idea, the ether was everywhere. It surrounded the Earth. It filled the empty regions between planets and stars. It extended throughout the entire universe, quietly carrying light from one place to another. It sounded like a clever solution, but the ether came with an impossible job description. It had to be rigid enough to support incredibly fast light waves. It had to be so transparent that planets could move through it without noticeable resistance. It had to exist everywhere, yet somehow remain completely invisible and almost impossible to detect. Still, for many physicists, it seemed like the only reasonable explanation. And if the ether truly existed, then the Earth should constantly be moving through it as our planet orbited the Sun. That motion should create something similar to a headwind. Imagine riding a bicycle on a calm day. Even though the air around you is still, you feel wind rushing against your face because you're moving through it. Scientists expected the Earth to experience something similar while traveling through the ether. This became known as the ether wind. If it existed, light traveling with the ether wind should take a slightly different amount of time than light traveling across it. The difference would be incredibly small, but with sufficiently precise instruments, it should be measurable. In 1887, two American physicists, Albert C. Michelson and Edward W. Morley, decided to put the prediction to the test. They designed one of the most precise experiments ever attempted. At its heart was a remarkable instrument called an interferometer. A beam of light was split into two identical beams. Each beam traveled in a different direction before reflecting off mirrors and returning to the starting point. When the beams recombined, they produced an interference pattern made of bright and dark bands. If one beam took even the tiniest fraction of a second longer than the other because of the Earth's motion through the ether, the entire interference pattern would shift. The predicted effect was extraordinarily small, but Michelson's instrument was sensitive enough to detect it. The scientific community waited with enormous anticipation. If the ether existed, this experiment should reveal it. The result: nothing. No measurable ether wind, no expected shift, no convincing evidence that the Earth was moving through any invisible medium at all. The experiment did not instantly destroy every existing theory. Science rarely changes overnight, but it left physicists with a deeply unsettling problem. One of the most carefully designed experiments in history had failed to detect the very thing many believed had to exist. The mystery ran even deeper. The real conflict was no longer about the ether itself. It was about two of the greatest scientific achievements of all time refusing to fit together. Newton's mechanics described motion with extraordinary success. Maxwell's equations described electricity, magnetism, and light with equal brilliance. Yet when combined, the two theories contradicted each other. According to Newton, speeds should add together. According to Maxwell, light appeared to ignore that rule completely. Both theories were spectacularly successful. Both matched countless experiments, yet both could not be fundamentally correct at the same time. Something had to change. Some physicists tried to preserve the old picture. Among them was the Dutch physicist Hendrik Lorentz, who developed mathematical transformations showing how moving objects might appear to shrink and how time itself might change just enough to explain why the speed of light always seemed constant. Meanwhile, the brilliant French mathematician Henri Poincaré recognized that these strange mathematical relationships hinted at something far more profound than anyone had previously imagined. The pieces of an entirely new understanding of reality were beginning to emerge, but no one had yet dared to ask the question that would change physics forever. What if the speed of light wasn't the thing that needed explaining? What if it was our understanding of space and time that had been wrong all along? In 1905, a young patent clerk working in Switzerland proposed an idea so radical that it would permanently change humanity's understanding of reality. His name was Albert Einstein. Unlike many great scientific revolutions, Einstein's breakthrough did not begin with a new machine, a larger telescope, or a more powerful experiment. It began with a question: what if the laws of physics look exactly the same to everyone moving at a constant speed? That idea wasn't entirely new. Galileo had hinted at it centuries earlier. If you're inside a smoothly moving ship with no windows, every experiment behaves exactly as it would if the ship was standing still. A dropped ball falls straight down. A pendulum swings normally. Water pours into a glass exactly as expected. There is no simple experiment that can tell you whether you are moving steadily or perfectly at rest. Einstein accepted that idea completely. Then he took one breathtaking step further. He proposed a second principle. The speed of light in a vacuum is the same for every observer, regardless of how fast the light source or the observer is moving. That single statement shattered more than 2 centuries of intuition. Think about how extraordinary it really is. Imagine standing beside a railway while an ultra-fast train races past. Someone standing inside the train switches on a flashlight aimed toward the front. Common sense tells you that the light should inherit some of the train's speed. After all, everything else does. Throw a ball, fire a bullet, launch a rocket. Their speeds combine with the motion of whatever launched them. Light refuses. Whether you're standing on the platform, riding inside the train, flying in a spacecraft, or observing from another planet, you always measure exactly the same speed for light traveling through empty space. Not almost the same, not approximately the same, exactly the same. If that sounds impossible, you are not alone. Physicists struggled with this conclusion because accepting it meant abandoning something they had trusted for centuries. If the speed of light cannot change, then something else must. Einstein realized that the quantities people had always assumed were fixed distance, and time could no longer remain absolute. Space could stretch, time could slow down. The measurements themselves depended on the observer's motion. Reality had not become inconsistent. Our assumptions about reality had. One of the first casualties was something so familiar that almost no one had ever questioned it. The idea of simultaneity. We instinctively believe that if 2 distant events happen at the same moment, then everyone in the universe should agree they were simultaneous. Einstein showed that this isn't true. Imagine a very long train moving smoothly along a straight track. A passenger stands exactly in the middle of the train at precisely the same instant. According to someone standing on the railway platform, 2 bolts of lightning strike the front and the back of the train. The observer on the platform is positioned exactly halfway between the 2 strike locations. Light from both lightning bolts reaches them at exactly the same moment. From their point of view, the conclusion seems obvious. Both lightning strikes happen simultaneously. Now consider the passenger standing in the middle of the moving train, while the light from both strikes is racing toward them. The train continues moving forward. That means the passenger moves toward the light coming from the front of the train and away from the light coming from the rear. Since light travels at the same speed in every direction, the passenger receives the flash from the front first and the flash from the rear slightly later. What conclusion should the passenger reach? Not that one beam of light traveled faster. Einstein's second principle forbids that. Instead, the passenger concludes that the lightning strike at the front must have happened before the one at the back. Both observers performed their measurements correctly. Neither made a mistake. Neither used faulty equipment. Neither misunderstood the laws of physics. Yet they reached different conclusions about whether the 2 events occurred at the same time. This is known as the relativity of simultaneity, and it is one of the deepest ideas in modern physics. There is no universal cosmic now. The present is not a single slice stretching across the universe that every observer shares. 2 observers moving differently may disagree about which distant events belong to the present, even while agreeing perfectly on every law of physics. This idea feels almost impossible to accept because human intuition evolved at speeds that are unimaginably small compared with the speed of light. In everyday life, these differences are so tiny that they become completely invisible. Our brains naturally construct the illusion of one shared present because, for ordinary experience, it works extraordinarily well. But nature itself plays by deeper rules. Once simultaneity becomes relative, another remarkable consequence follows almost automatically. If different observers cannot always agree on which distant events happen at the same moment, then they cannot always agree on how much time has passed between events either. Time itself becomes flexible, not because clocks malfunction, not because perception changes, but because time is woven into the very geometry of the universe, and that leads directly to one of Einstein's most astonishing predictions. A moving clock genuinely runs more slowly than one at rest. At first glance, the idea sounds almost impossible to believe. How could motion slow down time itself? Surely a moving clock only appears to tick more slowly because of the way we observe it, doesn't it? Einstein's answer was remarkably simple. No, the difference is real, not an illusion, not a trick of perspective, not a defect in the clock. A moving clock genuinely records less elapsed time than a clock that remains at rest relative to the observer. Comparing them to understand why, physicists often imagine one of the simplest clocks possible. A light clock. Picture two perfectly aligned mirrors facing one another. A single pulse of light bounces endlessly between them. Each round trip from the bottom mirror to the top and back again counts as one tick. If the clock is resting beside you, everything is straightforward. The light travels vertically between the mirrors. The distance never changes. Each tick takes exactly the same amount of time. Now imagine placing that same clock inside a spacecraft moving past you at an enormous speed. For the astronaut inside the spacecraft, nothing has changed. The mirrors remain perfectly still. The light continues bouncing straight up and down. Every tick feels completely normal. Nothing about everyday life inside the spacecraft seems unusual. The astronaut's heartbeat remains steady. Their thoughts flow naturally. Their biological processes continue exactly as they always have from their own point of view. Time has not slowed at all, but your view from outside tells a different story. As the spacecraft moves sideways, the light pulse can no longer travel straight up and down while the light moves between the mirrors. The entire spacecraft continues drifting forward. From your perspective, the light must follow a longer diagonal path instead of tracing a simple vertical line. It now forms a zigzag pattern through space. Here lies the crucial point. According to Einstein's second postulate, light always travels at the same speed. It cannot simply move faster to compensate for the longer distance. If the distance has increased and the speed remains fixed, then only one possibility remains. The journey must take longer. Each tick of the moving clock lasts slightly longer than each tick of the stationary one, and because every physical process inside the spacecraft is governed by time, everything slows together, not just the clock. Every chemical reaction, every heartbeat, every nerve impulse, every biological process, time itself has stretched. This phenomenon is called time dilation. It is one of the most extraordinary consequences of special relativity. Importantly, the astronaut never notices anything unusual inside the spacecraft. Every process slows by exactly the same amount. Their clock slows, their metabolism slows, even the neurons responsible for conscious thought slow together. Since everything changes at precisely the same rate, nothing appears different locally. The passage of time always feels perfectly normal from your own perspective. Time dilation only becomes visible when two observers who follow different paths later compare their clocks. The faster the relative motion becomes, the stronger the effect grows. At everyday speeds, the difference is unimaginably small. Walking across a room changes your experience of time by such a tiny amount that even the most advanced laboratory instruments struggle to detect it. Driving a car, flying in an airplane, even orbiting the Earth aboard the International Space Station, all produce measurable relativistic effects, but they remain incredibly small only as an object approaches the speed of light. As time dilation becomes dramatic, this relationship is described mathematically by the Lorentz factor, named after the Dutch physicist Hendrik Lorentz. At low speeds, the Lorentz factor is almost exactly equal to 1. Newton's familiar universe emerges naturally. Everything behaves just as common sense expects, but as speed increases, the Lorentz factor rises rapidly. Time slows more dramatically. Distances contract. The familiar universe begins to give way to an entirely different one. Remarkably, this isn't just an elegant mathematical prediction. Nature performs this experiment for us every single day, high above Earth's atmosphere. Energetic particles from deep space constantly collide with atoms in the air. Those collisions create unstable particles called muons. Muons resemble electrons but are much heavier. Left at rest, a muon survives for only about 2 microseconds before decaying into other particles. That lifetime is astonishingly short, even traveling at nearly the speed of light. Most muons should decay long before reaching Earth's surface, according to ordinary Newtonian reasoning. Very few should ever make it to the ground, yet they do, every second by the millions. Particle detectors at Earth's surface consistently observe far more muons than classical physics predicts. The explanation is beautifully simple from our point of view. The muons are moving at extraordinary speeds. Their internal clocks run more slowly relative to ours, although only a tiny amount of proper time passes for the muons themselves. Much more time passes in Earth's frame of reference as a result. They survive long enough to complete a journey that would otherwise be impossible. The universe itself confirms Einstein's prediction, and it doesn't stop there. In 1971, physicists Joseph Haffel and Richard Keating carried out one of the most famous real-world tests of relativity. They placed extremely precise atomic clocks aboard commercial airliners. Some aircraft flew eastward around the world, others flew westward. Identical clocks remained on the ground as references. When every clock was reunited and carefully compared, they no longer agreed that the airborne clocks had accumulated slightly different amounts of time. The differences were tiny, measured in mere billionths of a second, yet they matched Einstein's predictions with remarkable accuracy once both motion and gravity were taken into account. It was another quiet but unmistakable message from the universe. Time is not an abstract, philosophical idea. It is a measurable physical quantity. It stretches, it contracts, and it depends on the path an object follows through the cosmos. Every journey through space is also, in a very real sense, a journey through time. For ordinary human life, the effect is so small that we never notice it. A flight across the Atlantic will not make you visibly younger than the friends waiting at home. Even astronauts returning from months aboard the International Space Station have aged only fractions of a second less than people on Earth. But imagine replacing that spacecraft with one capable of traveling at 99% of the speed of light. Now the differences become astonishing. Years might pass on Earth while only months pass for those aboard the spacecraft. Travelers could return to a future that arrived far more quickly for everyone they left behind. This extraordinary consequence is known as the twin paradox, and despite its name, it isn't really a paradox at all. It is one of the clearest demonstrations that time is not universal, but deeply personal to the path each of us takes through spacetime. Imagine two identical twins standing side by side on Earth. They are the same age, their hearts beat at the same rhythm, their watches display exactly the same time. Every biological process inside their bodies unfolds in perfect synchrony. Now imagine that one of them boards a spacecraft capable of traveling at an incredible 99% of the speed of light. The engines ignite. The spacecraft accelerates. Within moments, it disappears into the darkness between the stars. Years pass. Eventually, the traveler turns around and begins the long journey home. When the spacecraft finally lands, the two twins embrace once again. But something astonishing has happened. The twin who remained on Earth is now significantly older. The traveler has aged much less. At first, this seems impossible. After all, motion is relative from Earth's perspective. The spacecraft moved away and later returned, but from the traveler's perspective, wasn't it the Earth that moved away? If each observer sees the other in motion, shouldn't each conclude that the other's clock ran more slowly? Why doesn't each twin return to find the other younger? This question became famous as the twin paradox, but the apparent contradiction disappears once we examine the journeys more carefully. The key lies in something far more important than speed alone. The two twins do not follow the same path through spacetime. The twin who remains on Earth stays, to a very good approximation, within a single inertial frame of reference. Their motion changes very little throughout the experiment. The traveling twin, however, experiences something fundamentally different. To leave Earth, the spacecraft must accelerate. To turn around, it must accelerate again. To slow down and land, it must accelerate once more. These changes mean the traveler switches between different reference frames. The symmetry between the two twins is broken. They are no longer describing identical situations from opposite viewpoints. They have taken entirely different journeys through the universe. This introduces one of the most beautiful concepts in modern physics: proper time. Proper time is the amount of time measured by a clock traveling along its own path through spacetime. Your wristwatch measures your proper time. So does your heartbeat, your breathing, your metabolism, the countless chemical reactions taking place inside every cell of your body. Proper time is, in the deepest physical sense, your own personal time. No observer can experience anyone else's proper time directly. Everyone carries their own clock through the universe. This is why the traveling twin never feels anything unusual. Their heartbeat remains perfectly normal, meals take the usual amount of time to eat, books require the same amount of reading, sleep feels exactly the same. Nothing inside the spacecraft seems slower because every physical process slows together. Only after returning to Earth and comparing clocks directly does the difference become undeniable. The traveler's clock simply records fewer years, not because it malfunctioned, not because it was damaged, but because the path it followed through spacetime contained less proper time. One of the easiest ways to picture this is by imagining two hikers. Both begin at the same mountain cabin. Both eventually arrive at the same summit, but they choose different routes. One follows a direct trail, the other wanders through forest, circles a lake, climbs an extra ridge, and eventually reaches the same destination several hours later. They shared the same starting point. They shared the same ending point. Yet they did not travel the same distance. Relativity reveals something equally remarkable. Two observers can begin together, separate, take entirely different routes through spacetime, and reunite having experienced different amounts of time. The geometry of spacetime determines the result. Time is no longer a universal river carrying everyone forward equally. It becomes something woven into the shape of each journey. This insight became dramatically clearer in 1908, when the mathematician Hermann Minkowski proposed a revolutionary way of understanding Einstein's theory. Until then, space and time were still often imagined as separate ingredients. Minkowski argued that separating them was a mistake. Instead, he declared something that would permanently transform modern physics. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a union of the two will preserve an independent reality. His idea was breathtakingly elegant. The universe is not made of three dimensions of space with time flowing independently beside them. Instead, everything exists within a single four-dimensional structure known as spacetime. Every event in the universe is defined by four coordinates. Three describe where it happens. One describes when it happens. Neither is complete without the other. Knowing where a supernova exploded means little if we don't know when. Knowing when a distant star emitted its light means little unless we know where that star was located. Every event occupies a unique position within spacetime. This completely changes the way we think about motion. Objects no longer simply move through space while time flows beneath them. Instead, every object traces a continuous path through spacetime. Physicists call this path a world line. Your entire life from your first heartbeat to this very moment is represented by a single continuous world line stretching through the four-dimensional universe. Every choice you make, every journey you take, every second you experience extends that line a little farther. Different observers follow different world lines. Some remain close together, others separate by billions of kilometers. Some eventually cross again, and when they do, they can compare how much proper time each path contained. Suddenly, time dilation is no longer a mysterious side effect of moving clocks. It becomes a natural consequence of geometry itself. Just as two different routes across a landscape can have different lengths, two different world lines through spacetime can contain different amounts of elapsed time. The twin paradox isn't strange because clocks behave oddly. It is strange because the geometry of reality itself is unlike anything our everyday intuition prepared us to expect. But Einstein's revolution was still incomplete. Special relativity described observers moving at constant speeds through empty space. It deliberately ignored one of the most familiar forces in the universe, gravity, and gravity was about to reveal an even deeper secret. Because if motion can slow the passage of time, what happens when gravity itself begins to bend spacetime? For centuries, gravity seemed wonderfully straightforward. Drop a stone, and it falls. Throw a ball into the air, and it eventually comes back down. The moon circles the Earth. The Earth circles the Sun, according to Newton. All of these motions were produced by an invisible force acting across space. Mass attracted mass, the larger the mass, the stronger the attraction. It was an elegant theory that explained everything from falling apples to the motion of planets with astonishing accuracy. Yet even Newton admitted there was something deeply mysterious about it. How could one object pull on another across empty space? What was actually carrying this force from one body to another? Newton himself refused to speculate. He simply described gravity with extraordinary mathematical precision, even if its underlying mechanism remained unknown. More than 2 centuries later, Einstein looked at the same mystery from an entirely different perspective. Instead of asking what force pulls objects together, he asked a far more radical question: what if gravity isn't really a force at all? That single question led to one of the greatest scientific achievements in history. In 1915, Einstein completed the general theory of relativity. It didn't merely improve Newton's theory, it completely reimagined gravity itself. According to general relativity, matter and energy do something extraordinary. They change the geometry of spacetime. Mass doesn't simply sit inside spacetime. It tells spacetime how to curve, and curved spacetime tells matter how to move. John Archibald Wheeler would later summarize the entire theory in one unforgettable sentence: matter tells spacetime how to curve, and spacetime tells matter how to move. Although beautifully simple, this idea is remarkably difficult to visualize. Imagine placing a heavy bowling ball on the center of a stretched rubber sheet. The sheet bends beneath its weight. Now roll a marble across that surface. The marble curves toward the bowling ball not because an invisible hand is pulling it sideways, but because the surface beneath it is no longer flat. The marble is simply following the straightest path available on a curved surface. This analogy isn't perfect. Real spacetime is 4-dimensional, not a rubber sheet lying in ordinary space, and gravity isn't caused by something pulling objects downward into another dimension. Still, the image captures the essential idea. Mass changes geometry. Geometry changes motion. The Earth isn't orbiting the Sun because some invisible rope continuously drags it around. Instead, the Sun's enormous mass curves the surrounding spacetime. The Earth follows the natural path through that curved geometry. Likewise, when an apple falls from a tree, it isn't being mysteriously pulled downward in the old Newtonian sense. It is following the straightest possible path through curved spacetime toward the Earth. That realization alone would have been revolutionary. But Einstein's equations contained an even more astonishing prediction. If gravity changes the geometry of spacetime, then it cannot affect space without also affecting time. Time itself must curve. Time itself must slow down. The stronger the gravitational field, the more slowly time passes. This phenomenon is known as gravitational time dilation. Imagine 2 perfectly synchronized atomic clocks. One remains at sea level. The other is carried to the top of a very high mountain. Leave them there for weeks, months, perhaps even years. When the clocks are reunited, they will no longer agree. The clock that spent its time higher above the Earth will have recorded slightly more time. It will be ahead. The clock closer, the Earth's center where gravity is stronger, will have experienced time more slowly. The effect is incredibly small. No human being could ever notice it without extremely precise instruments. But atomic clocks can. In fact, modern clocks are so accurate that they can detect changes in the passage of time caused by differences in height of only a few centimeters. Think about what that means. Raise a clock by the height of a coffee mug, and it experiences time ever so slightly faster. Reality is that sensitive. The higher you are in a gravitational field, the faster your clock ticks, the deeper you descend into gravity, the slower time flows. Unlike ordinary intuition, the universe does not possess one universal rate at which time passes. Every clock follows the geometry of the spacetime surrounding it. At first, this sounds like an elegant curiosity with little practical importance. But if Einstein had been wrong, much of modern technology would simply fail. Consider the Global Positioning System, better known as GPS. More than 30 satellites orbit the Earth, each carrying incredibly precise atomic clocks. Your phone determines its position by comparing signals arriving from several of these satellites. Those signals travel at the speed of light. Even tiny errors in time quickly become enormous errors in location. The satellites orbit roughly 20 kilometers above Earth's surface. At that altitude, Earth's gravity is weaker than it is on the ground. As a result, The satellite's clocks naturally tick faster, however. The satellites are also moving at nearly 14 kilometers per hour. And special relativity predicts that motion slows their clocks. Two different relativistic effects are occurring simultaneously. Motion slows the clocks, weaker gravity speeds them up. When both effects are calculated together, the satellites gain approximately 38 microseconds every day compared with clocks on Earth's surface, 38 millionths of a second. It sounds insignificant, but if engineers ignored that tiny difference, GPS errors would grow by nearly 10 kilometers every single day. Within a short time, navigation systems around the world would become almost useless. Your phone would tell you that you're driving through buildings. Aircraft would drift off their intended routes. Ships would slowly accumulate dangerous positioning errors. Relativity isn't an optional correction. It is built into the technology millions of people depend upon every hour of every day. Einstein's equations quietly guide every GPS signal crossing the sky. Few people ever think about it. Yet every successful navigation request is another confirmation that gravity truly changes the passage of time. And if Earth's relatively gentle gravity can produce measurable time differences, imagine what happens near something far more extreme. Imagine a star so dense that a teaspoon of its material would outweigh a mountain, or something stranger still, a place where gravity becomes so overwhelming that not even light can escape, a place where time itself seems to approach a standstill. That place is called a black hole, and it pushes our understanding of time to its absolute limit. Few objects in the universe capture the imagination quite like a black hole. The name itself suggests an empty void, a dark region in space that swallows everything that comes too close. But a black hole is not our hole in the ordinary sense. It is a region of spacetime where gravity becomes so extreme that escape is no longer possible, not for spacecraft, not for planets, not even for light. To understand how extraordinary this is, imagine compressing the entire mass of our sun into a sphere only a few kilometers across. Nothing magical has been added. Nothing mysterious has appeared. The mass remains exactly the same, only the density has changed. Matter has been compressed so tightly that spacetime becomes warped beyond anything we experience in everyday life. At the heart of every black hole lies a boundary known as the event horizon. It is often called the point of no return. Cross it, and every possible path through spacetime leads inward. There is simply no route back out, not because an invisible barrier blocks your escape, but because spacetime itself has become so dramatically curved that every future direction points toward the center. This idea is almost impossible to picture, because our intuition evolved in a universe where space is only gently curved, near a black hole. That intuition is no longer reliable, yet perhaps the strangest effect is not what happens to space. It is what happens to time. Imagine an astronaut approaching a black hole while another astronaut watches safely from far away. The traveler carries a perfectly accurate atomic clock every second. The clock sends a pulse of light toward the distant observer. At first, those pulses arrive exactly 1 second apart. But as the traveler gets closer to the event horizon, something remarkable begins to happen. The signals arrive farther and farther apart. 1 second, then slightly more than 1 second, then 2, then 5, then 10. The distant observer. The traveler's clock appears to slow dramatically. Every heartbeat seems delayed. Every movement becomes slower. Every spoken word stretches into silence. As the astronaut approaches the event horizon, the effect grows stronger and stronger from the outside observer's perspective. The traveler appears to move almost in slow motion. Eventually, the clock seems nearly frozen. Its signals become weaker, redder, and increasingly difficult to detect. As the light loses energy, while climbing out of the black hole's immense gravitational field, this effect is known as gravitation redshift. The light itself is stretched to longer wavelengths as it escapes the intense curvature of spacetime. To someone watching from a safe distance, it appears as though time itself has almost stopped. But here is the astonishing part. The astronaut falling toward the black hole experiences nothing unusual. They watch ticks normally. Their heartbeat remains steady. Their thoughts unfold at the usual pace. They do not feel time slowing. They do not feel themselves freezing from their own perspective. They simply continue falling. This is one of the deepest lessons of relativity. Time is always local. every observer experiences their own proper time. Normally, the dramatic differences appear only when observers following different paths compare their clocks. This often leads to a common misunderstanding. People sometimes ask, if time stops at the event horizon, does the astronaut become trapped there forever? The answer depends entirely on who is asking the question. From the viewpoint of the distant observer, the astronaut appears to approach the event horizon more and more slowly. The final crossing never seems to occur within a finite amount of the distant observer's time. Instead, the astronaut gradually fades from view as the escaping light becomes weaker and more redshifted. But from the astronaut's own perspective, nothing special happens exactly at the event horizon. There is no invisible wall.no sudden impact.no dramatic flash announcing the crossing. If the black hole is large enough, they could pass through the event horizon without immediately noticing anything unusual. Only much later, as they continue falling toward the center, would the increasingly powerful tidal forces begin to dominate. These tidal forces arise because gravity is not equally strong everywhere. The side of your body closer to the black hole feels a slightly stronger gravitation pull than the side farther away, near Earth. This difference is tiny. It is responsible for the ocean tides near a black hole. The difference can become unimaginably powerful if the black hole is relatively small. Those tidal forces grow so intense that they stretch anything falling inward. The feet experience a stronger pull than the head. The body gradually becomes longer while being compressed from the sides. Physicists gave this dramatic process an unforgettable name: spaghettification. The name sounds amusing. The physics behind it is anything but. For enormous supermassive black holes, however, the situation becomes surprisingly different, because the event horizon lies much farther from the central singularity. Tidal forces at the horizon can actually be quite gentle. An astronaut might cross the event horizon without experiencing any immediate physical harm. The truly destructive forces would come much deeper inside. Black holes reveal something profound about time. The stronger gravity becomes, the more dramatically the flow of time changes. Near Earth's surface, the effect is tiny. Near a neutron star, it becomes significant. Here, a black hole, it becomes extraordinary. Yet even this is not the end of the story. Black holes force physicists to confront an even deeper mystery. According to general relativity, matter falling into a black hole eventually reaches a region where spacetime appears to become infinitely curved, a point known as a singularity. Infinity. In physics, infinity is often a warning sign. It usually tells us that a theory has reached the limit of its usefulness. General relativity describes gravity with astonishing precision across enormous distances. Quantum mechanics describes the microscopic world with equal success, but inside a black hole, those two great achievements of modern physics refuse to cooperate. General relativity predicts one thing, quantum theory demands another. Both cannot remain complete under such extreme conditions. Somewhere beyond the event horizon, hidden from observation, the two pillars of modern physics collide. That collision tells us something profoundly important. Our understanding of time is still incomplete, despite everything Einstein discovered, despite every experiment confirming relativity, despite every satellite quietly correcting its clocks. The deepest nature of time remains one of the greatest unsolved mysteries in science, because the question is no longer simply, how does time flow? It has become something far more fundamental. Why does time seem to flow in only one direction? That question may be the strangest of them all. Why does time seem to move only forward? Every moment of our lives reinforces the same experience. We remember the past. We do not remember the future. A shattered glass never leaps back onto the table. Smoke drifts away from a candle, but never gathers itself back into the flame. Ice melts into water. It never spontaneously freezes into a perfectly shaped cube inside a warm room. Everything around us seems to agree that time has a preferred direction. Physicists call this the arrow of time. But here's the remarkable part. Most of the fundamental laws of physics don't actually care which direction time points. Take Newton's equations. If you recorded two planets orbiting each other in deep space and played the video backward, the motion would still satisfy Newton's laws. Nothing in the equations themselves tells you whether the film is running forward or in reverse. The same is true for Maxwell's equations describing electricity and magnetism. Even the Schrödinger equation at the heart of quantum mechanics is largely symmetric with respect to time. At the microscopic level, nature often appears surprisingly indifferent to the distinction between past and future. So where does the arrow of time come from? Why does everyday life look so different? The answer leads us into one of the most important ideas in all of physics: entropy. Entropy is often described as a measure of disorder, but that simple definition can be misleading. A better way to think about entropy is as the number of possible microscopic arrangements that correspond to the same overall appearance. Imagine opening a brand new deck of cards. There is essentially one perfectly ordered arrangement. Now shuffle the deck thoroughly. How many random arrangements are possible? Not thousands, not millions, more than 10 different combinations. The overwhelming majority of those arrangements appear random. Perfect order is extraordinarily rare. Disorder is overwhelmingly probable. The same principle applies throughout nature. Suppose you drop a jigsaw puzzle onto the floor. The pieces scatter everywhere. Could they, in principle, bounce back together into a completed picture? The laws of physics don't absolutely forbid it. Every piece could, theoretically, follow exactly the right path, but the probability is so unimaginably tiny that it will almost certainly never happen, not even if the universe lasted trillions upon trillions of times longer than its current age. This is the essence of the second law of thermodynamics in an isolated system. Entropy tends to increase, not because nature prefers disorder, not because some invisible force pushes everything toward chaos, but because there are simply far more disordered arrangements than ordered ones. Imagine placing a single drop of blue ink into a glass of clear water. At first, the dye occupies only a tiny region. As time passes, the ink spreads throughout the glass. Eventually, it becomes evenly mixed. Now ask yourself the reverse question. Why doesn't the ink spontaneously gather back into a single drop? The molecules certainly continue moving. They continue colliding. Nothing prevents them individually from wandering back toward the center, but the number of possible mixed arrangements is astronomically larger than the number of perfectly unmixed arrangements. Random motion overwhelmingly favors mixing. Order is statistically fragile. Disorder is statistically inevitable. This statistical tendency gives time its apparent direction. The future is the direction in which entropy increases. The past is the direction in which entropy was lower. Remarkably, this means the arrow of time may not be built directly into the fundamental equations themselves. Instead, it may emerge from the universe's extraordinarily unusual beginning. When the universe was very young, shortly after the Big Bang, it existed in an incredibly low entropy state. That fact remains one of the deepest mysteries in cosmology. Why did the universe begin in such an extraordinarily ordered condition? No one knows. Yet that single fact appears to shape everything we experience. Stars shine because they move toward higher entropy. Living organisms survive by exporting entropy into their surroundings. Weather systems evolve because energy spreads. Galaxies form. Mountains erode. Memories are created. History unfolds. Even your brain forms memories by irreversible physical processes that increase entropy. You remember yesterday because traces of yesterday remain encoded in the present. Tomorrow has left no such traces. Memory itself points toward increasing entropy. This idea is profoundly different from saying time is merely an illusion. The passage of time feels real because physical processes genuinely unfold. Clocks continue ticking. Particles continue interacting. The universe continues evolving, but the direction we call forward may arise not from the fundamental laws themselves, but from the universe's remarkably special initial conditions. This realization raises an even deeper possibility. Perhaps what we experience as the flow of time is not a fundamental ingredient of reality at all. Perhaps it is an emergent property, something that appears naturally when enormous numbers of particles interact. Just as temperature emerges from the collective motion of atoms, could time itself emerge from something even more fundamental? Some of today's leading theories suggest exactly that. In certain approaches to quantum gravity, spacetime may not be the deepest layer of reality. Instead, space and time themselves could emerge from more primitive quantum relationships that do not resemble either space or time in the ordinary sense. If that idea proves correct, then Einstein's spacetime remarkable as it is may not be the final chapter. It may be another layer in an even deeper structure waiting to be discovered. That possibility reminds us of something both humbling and inspiring. Every great revolution in physics has revealed that reality is stranger than anyone expected. Newton showed that the heavens and the earth obey the same laws. Einstein revealed that space and time are woven together. Quantum mechanics uncovered a microscopic world governed by probabilities rather than certainty. Each breakthrough answered odd questions, while uncovering even greater mysteries, and time remains at the center of them all. We measure it with extraordinary precision. We build civilizations around it. We organize every moment of our lives according to it. Yet we still cannot say with complete confidence what time truly is. Perhaps one day, a new theory will unite quantum mechanics and gravity into a single framework, revealing the deepest nature of spacetime itself. Perhaps it will explain why the universe began in such an incredibly ordered state. Perhaps it will even reveal that time, as we experience it, is not fundamental at all. Until then, one truth remains unavoidable. Every heartbeat, every sunrise, every distant galaxy whose light has traveled billions of years to reach our eyes, every memory we carry, and every future we have yet to experience, is part of one of the greatest mysteries the universe has ever offered. We spend our lives measuring time, but perhaps the greater challenge has always been understanding what, exactly, is doing the passing.